You have a sick limit, take it to the limit hospital. So if your limit is sick in this specific way, then I can write it as a quotient that turns into 0 over 0 or infinity over infinity, doesn't matter the sign. Then that limit I can rewrite as the derivative of f, derivative of g, and the limit's the same. That's LHopitals' rule. A is allowed to be infinity. It's kind of a key observation we'll be making use of quite often. 0 is really 1 over infinity. 1/100th, 1 over 100, and vice versa. So there's only one case we have to really think about is 0 over 0, because infinity over infinity is 0 over 0. Also, infinity times 0 is 0 over 0. So if we're proving it, that's all we really need to focus on. I only need 2 examples because for the elementary functions, powers, exponentials, sines, cosines, it's just powers and exponentials that grow. So our first example with the exponential. 0 is really a 1 over infinity. And I'll make use of the fact that any number is a double reciprocal of itself to throw things into the denominator. Now I have infinity over infinity, and I can do LHopitals' rule. Derivative of x, derivative of the exponential. Here, of course, f over g is really f times 1 over g, and the same for the derivative. So LHopitals' rule is telling us that exponential goes to 0 much faster than x goes to infinity. Let's look at powers and natural logs. How did I know to do the double reciprocal on the exponential? I didn't. I actually did both ways and found which way was better. Let me show that process for this example. How do I know which one to double reciprocal? First I'll do double reciprocal on the x, and then I'll do double reciprocal on the natural log. Rewrite as powers to make derivatives a little simpler. So these are both L'Hopital style. So after I apply L'Hopital, in the first case, it's 1 over x divided by minus x to the minus 2. And on the other case, it would have been chain rule. So I got to chain along the derivative of the natural log. So in the first case, it's all powers of x. Everything simplifies nice. In the other case, it's a mixture of natural logs and powers. Yeah, it doesn't simplify, not so much. Now that we have our game plan, we execute. Take our limit, double reciprocal the x, and rewrite it as a power. L'Hopital. Derivative of natural log, and derivative of the power. Collect my x's, and plug in 0. Real briefly, let me just do that algebra. I'm running everything as powers. -1 power and a 2 power. Let's do the proof of 0 over 0. Here's what we want to get to, is that the limit as x goes to a of f over g is the limit as x goes to a of f prime over g prime. We're going to use the mean value theorem to connect it. And we're going to change a variable as well. So mean value theorem, C is some number between x and a. I don't know where it is. Good for G, same way. I'll use the same C, which I have to prove I can do. So when I divide and plug in that f of a and g of a are both 0, there's my connection. Now, as x goes to a, c is sandwiched in between, so c goes to a. This really limits c goes to a, f prime c over g prime c, relabel c as x, and we have it. I'm going to start with what I want and work backwards. So what I want is f prime over g prime at the same c to be this quotient. So I'm going to construct a function to make that work. So this is what I want to happen. Get a common denominator, collect everything to the same side, and I'll call that function h prime. The function of c, x and a are constants, so this is going to be an easy antiderivative. So I want h prime to be 0, so I need to construct an h to make this work out through a mean value theorem. Antiderivative in c, f plus a constant, which I'll put in a second, constants, g plus a constant times another constant. I want to plug in x and get 0. So plugging in x for c, I've got an f of x. So if I do f of x minus a, those terms will cancel. And a g of x minus g of a, those terms will cancel. Plugging in a, they just cancel immediately. Mean value theorem, and there's some point c in between where the derivative is 0. The only thing left is the infinity cases. If a is infinity, that one's easy. I do x is 1 over t. Driving x to infinity drives t to 0, which we just did. F over g is infinity over infinity. It's a little trickier, but it's not too bad. I do the same trick I did in both examples. I'll double reciprocal the f. And now it's a 0 over 0 case, which we know the mean value theorem applies to. So doing the mean value theorem, doing the LHopitals rule for the 0 over 0 case, little chain rule, clean up the algebra, so my LHopitals rule on f over g gave me f over g squared g prime over f, which is 1 over f prime over g prime. So in the limit, that's some number. That's the same number squared, and it's 1 over our f prime g prime. Well, immediately then, the limit of f prime over g prime has to be L, which is the limit of f over g.